Engineering mistakes can lead to a high-profile disasters. That is why engineers need to optimize and stress test the design. Doing so can save millions on iterative prototyping with physical materials. What is a finite element analysis, by the way? A finite element analysis is a way of mathematically modeling the stresses on an engineering design. Engineers can apply FEA to any physics problems. We can model mathematically, and that includes a structural analysis, fluid dynamics, and a heat transfer. The importance of a finite element analysis is that it's able to take a complex design and offer insight into its efficiency and robustness of the design. With finite element analysis, engineers can gain early information on system failure and improper design technique. Now we will discuss the finite element method. The finite element method involves constructing a digital mesh of the design, like what we can see in the figure here. This design includes of a smaller element, and these smaller elements are what we call as finite elements. So we can then map data for each of the finite elements. And this breaks large-scale equations into a small equation for each element. And this equation then can combine to give a picture of the dynamic acting on the design. Typically, the smaller the mesh size, the more accurate the solutions, as the design a beta sample across the physical domain. The equations usually required for this kind of a calculation are often a partial differential equation, or PDE. With a finite element method, these PDEs break down into a simpler algebraic approximation. So what are the benefits of a finite element analysis? Finite element analysis, or FEA, allows engineers to prototype a design in action without the need to create a physical working model. The nature of a FEA offers a few more advantages. The use of finite elements allows the modeling of multiple material types, testing of a complex geometry, and the ability to capture the local effect acting on the small area of the design. So, in practice, engineers can use the finite element modeling software on a variety of tasks. The information of a current impact, like what we can see here, stresses on a human joint, and fluid dynamics over turbine are just a few examples of some of the applications of a finite element analysis. But we have to remember that finite element analysis is just a predictive model. It doesn't confirm that a design will survive the model stress, but it gives engineers a clearer picture of how the design will react to stresses and reduces the need for extensive prototyping. As a conclusion, we can say that finite element analysis is a very powerful tool for many applications in engineering, and effective use of a finite element analysis can save companies time and money through mathematical prototyping. Finite element analysis is just one of the digital technologies transforming the future of engineering. The practical advantages of using a finite element analysis have led many sectors to make it fundamental part of their design process. With a finite element simulation, many design iterations are no longer dependent upon the machine shop and manufacturing schedule. And hence we can have a faster and less expensive design cycle. Each new design can be virtually tested in hours instead of waiting days or weeks for a hard copy to be tested.